Okay. All right, so let's start. Assalamualaikum and good morning for those who just joined. All right, so for today, we will continue our from our previous class yesterday, which is, bipolar junction transistor, still the same chapter, DC analysis, but for today, we will focus more on the fixed base bias with emitter resistor, where there's an emitter resistor, where this is also called as emitter stabilized bias circuit. Okay, so we will discuss about the load line analysis for the emitter, the stabilized circuit, and also we will discuss about another circuit, which is a voltage divider bias circuit, and we will discuss about the load line analysis for this circuit. And also for the PNP BJT. All right, so all right, okay, for those who just joined, I show to you. You can scan the QR code for the class attendance. Okay. You can scan the QR code for the class attendance first. Okay. All right. Okay. Finish here. All right. Okay, so stop this one. Okay, so a little bit quick recap from yesterday class. So the yesterday we learned about fixed base bias. All right, fixed base bias circuit. So to solve this circuit, first of all, you need to know you need to divide the BE loop and the CE loop. Okay, after you remove or replace the capacitor with an open circuit. Okay, so you need to identify the BE loop and the CE loop, and then from here you need to use the Kirchhoff voltage law to solve the equations. So you will get the IB. Okay, for you to know the value of currents that flow from the base at the base. So this is the formula. Okay, IB equals to VCC minus VBE divided by RB. Okay, which is the resistor value at base, and then the value for current at the collector also can be calculated using this value here. So this is actually IB. All right. So the voltage at the base, collector, and emitter can be calculated using this here. VC equals to VCC minus ICRC, VB equals to VCC minus IB, RB. All right. So load line analysis, okay, from here, okay, sometimes they ask you to plot the load line, make a load line, right? So how to do the load line plotting, right? So first of all, you need to use same KVL and output loop, so you will get VCE equals to VCC minus ICRC, and we need to assume that IC equals to 0 milliamps. Okay, so from here you will get VCE equals to VCC. So this is the intersect for the axis. Okay, so also known as the cutoff value. And next, So once you know the x-intercept for the x-axis, right? Next, you need to find the y-intercept for the y-axis, right? So to find that, so you have to assume that VCE equals to 0. So this is during the saturation. So IC will be equals to VCC divided by RC. So this is the value for intersection at the y-axis, yeah? And also this is known as the saturation point, yeah? Saturation point, yeah, saturation value. So, and then by knowing these two intersections, then what you have to do is just to connect, yeah. By joining these 2 points defined by step 2 and 3, you get straight line that can be drawn in the figure. All right. So this is just a little bit recap for yesterday's class, yeah. So for today, we're going to look about fixed bias with emitter resistor. Also known as emitter stabilized bias. So as we know yesterday, okay, as I mentioned, that the disadvantage of the fixed base bias circuit, okay, the beta, okay, the beta value is depending to the, sorry, not the beta. The currents at the collector is depending for the beta value. So the beta value can be changed with the, when the temperatures change, okay, when the temperature change, so it is not good, okay, so it is not stable enough. So to make the circuit stable, okay, so emitter stabilized bias is introduced, okay, wait. So emitter stabilized bias, okay, you can see what's the difference between the fixed base bias, okay, they just add, okay, a resistor, okay, resistor is added at the emitter part. Okay, before there's no resistor at the emitter part, but for this, for the emitter stabilized bias, there is a resistor added at the emitter part, and this resistor is always known as RE, okay, resistor at emitter. For RB, resistor at base, and RC is resistor at collector. Okay, so an emitter resistor RE is added to improve the stability. So this circuit, okay, this circuit can be solved using KVL, Kirchhoff voltage law, same as before. So for you to solve this kind of circuit, okay, the method is same. Okay, first of all, we need to locate the capacitor. Okay, locate the capacitor and replace with open circuit. Okay, so ignore this capacitor. Okay, so we replace this capacitor with the open circuit. And then we will locate 2 main loops. Okay, you need to locate 2 main loops, same as previous. Okay, first the BE loop and then the CE loop. Okay, so let's look into detail. Okay, so first step, okay, locate the capacitors and replace with an open circuit. Okay, so there are 2 capacitors at this circuit, okay, usually okay, at the input and at the output. Okay, there are 2 capacitors. So what you need to do is to remove this part. Okay, make this part as an open circuit. Make this part as an open circuit. So it means that there's no current flow here. Okay, no current flow, and we ignore this part. Yeah. So when you remove this, it will be like this. Okay, the circuit will be like this, and or you can also draw like this, yeah. So VCC to RB, VCC to RC. So this is the base part. So this is the collector part, and this is the emitter part. Okay, either one is okay. All right. So this is the current flow that from IB at the base, and this is the current flow at the IC at the collector, and this is going to be the current flow IE at the emitter. All right. So I think this is same as before. So once you have removed the capacitor, you need to locate the main loops, okay, for the BE loop and also for the CE loop. So for the BE loops, it's gonna look like this, yeah. So VCC, okay, currents flow from here, okay, positive VCC here, and then we'll enter RB, okay, resistor at the base here, and then we'll enter the, okay, so currents enter from here, so this is going to be positive, and currents come out here, so it's going to be negative. So this is going to be positive, and this is going to be negative. This is going to be positive and this is going to be negative. All right. So this is the BE loop. And then next, CE loop. All right. So this is currents enter here, positive, and then negative. And then currents enter here, positive. And then currents come out here, negative. Enter here, positive, and then negative here. So this is the CE loop. Okay, next, what you need to do is analyze the BE loop. Okay, so same as yesterday. Okay, we need to use the Kirchhoff voltage law. All right. So for this, choose one loop. Okay. So usually it's easier to use the anti-clockwise loop, from the source of the battery. But you also can use this loop. Okay, any loops is fine. So if you are using this kind of loop here, anti-clockwise loop, so it will be VCC minus, okay, because this is plus, this is minus, this is plus, and this is minus, right? And then this is plus, this is minus. So VCC minus IBRB minus VBE, okay, minus VBE here, minus IERE. Okay, we will take at the end of the currents, yeah. So VCC minus voltage drops at the resistor RV, and then voltage drop at the VBE part, and then voltage drop at the IERE, at the emitter part, resistor at the emitter part. Okay. So this one, we need to know IE equals to beta plus 1 IB, all right? So I think yesterday also I already mentioned about this, IE is equals to beta plus 1 IB. Okay, so this is current at the emitter. Okay, beta plus 1, beta usually is given. All right, and then times with the value of currents from IB, all right? And then once you get this, all right, we need to substitute into this equation, okay, IE here. So you need to, once you replace, it's going to be like this, right? So from here, we can find the value of IB. Okay, from here, okay, so you need to rearrange this equation. So you can find the value of IB. So you will get IB is equals to VCC minus VBE divided by resistor value at the base plus beta plus 1, and then this value times with the resistor at the emitter part. All right. So what's the difference between the fixed bias configuration equation of IB? So you can see that the difference is for emitter stabilized bias circuit, there is an addition of this part. Okay, beta plus 1 RE. Okay, so others is same, only at the divide part, division part from here. For bias configuration, we only consider about the resistor at the base. Okay, but for the emitter stabilized bias circuit, you need to consider as well the resistor value at the emitter. So this is the only difference, okay, from these two circuits. All right. Next, for the CE loops, okay. So CE loops analysis. Okay, first of all, same as well as BE, we need to consider the Kirchhoff voltage law as well. Okay, so since that the current is flowing, okay, we decide that the current is flowing from up to down. Okay, so we also can decide currents flow from down to up, no problem. Okay, with any direction is fine. Okay, you will get the same answer. Okay. So from here, this is positive, this is negative, currents enter here positive, currents come out here negative, currents enter at the resistor here positive, currents come out here negative. All right, so VCC minus ICRC, potential drop at the resistor at the collector here, and then minus with the potential drop at the collector emitter here, part here, and then current potential drop at the resistor at the emitter here. All right, so we assume, okay, we need to assume that IE, okay, currents that flow at the emitter is almost the same, okay, approximately same with the current flow at the collector here. Okay, so since that there is no resistor here. Okay, actually there is a resistor, but the value is very small. So we assume that the current flow IE is almost equals with the current flow at the IC. Okay, current flow at the emitter is almost same with the current flow from the collector. So as we assume this, so the value of VE, right, at here, yeah, at here, VE here is equals to IE RE, right? IE RE. So VCE, okay, for you to know, for us to know the this is the VC, this is VE. For us to know the value of VCE, so it means that the potential, usually the potential is here is higher compared to the potential here, right? So VC minus to potential of VE. Okay, VC minus potential of VE. So next, since that we know the potential of the potential, since we want to find VC, VCE is sometimes given. Okay, VCE, VC, so you can rearrange, yeah, from here you can rearrange in for what you want to find. Okay, so if you want to find VC, so it equals to VCE plus VE, or you can always say VCC minus ICRC. Okay, where this is the value of potential drop here. Okay, ICRC, and then VCC here. Okay, so for you to find VC here, you can use the value of VE plus with the VCE, or you can also use VCC minus with the potential drop here. Okay, so there are two ways. Okay, decide with what information that you have. Okay, what value that you have. Okay, so let's say that you have the value of VE, okay, and VCE. So it means that you can use this equation to find VC. But once you once you don't have this value, but you have the VCC value, usually VCC value is given. Okay, you have the VCC value, and then we know that IC value, even though it is not given, but we know that IC is equals approximately with IE, and you know IE, all right? So you can use this equations, yeah? You can use these equations. For this equation as well, let's say that you don't know that what is the value for IE, but we know that IE is approximately to IC. So we can say that VE is equals to IC RE. Okay, since that IE is approximately to IC. So in exam also, you need to mention this, yeah? Assume IE is equals to, or approximately equals to the IC value, because sometimes, yeah, this, when you write this information will give you marks. Okay, all right, yeah, please write this as well in your exam. Okay, so let's say that your answer is wrong, but you have this kind of information, yeah, you have this kind of information. So lecturers are going to give you marks for this information, yeah. And also, let's say your calculations down here is wrong, but you have this information, so there are going to be marks for this information as well. So don't skip any methods, yeah, right? The methods accordingly, right? Because each of the methods, sometimes there is marks for that, yeah. So for you to find VB, okay, VB, V at B here, okay, VB here. So VCC value here minus with this is from the loop, from BE loop, okay. There's a emitter here, right? Okay, so for us to find VB value, so VB is VCC divide with minus with the potential drop at the resistor RB. So you will get the value for VB. Okay, or let's say that there is no information for VCC here, but we have information of BE here. Okay, usually we know the value of VBE, right? Because VBE is always constant, okay, at 0.7. Okay, so we know the value of VBE here, and we know the value of VE here. Okay, we know the value of VE here, where VE is IE, RE, where IE is same with IC, so IC, RE. So since that you know all this information, you can also use these equations. Yeah. So decide which equation that you want to use based on what information that you have. All right. So therefore, VCE is equals to, okay, the value for VCE equals to VCC, okay, VCC minus with this, yeah, minus with IC, RC, okay, plus, okay, plus with, minus as well, minus with ICRE. Okay, kalau let's say we expand this equation, you will get BCC minus ICRC minus ICRE, where this is the potential drop at the resistor RE, this is the potential drop at the resistor RC. Okay, so you will get the value of BCE here. All right. So next, okay, I hope until here is okay. Yeah? All right. Next, let's look at the example. Okay, example. I think I didn't delete the answer in your handout because I think it's quite difficult for you to take note during the lecture. So please refer to the answer as well. Okay, so this is the example. Find IB. Where is IB? IB is current step flow here, yeah? IB. And then IC. IC is current that flow here. IC. And then VCE. VCE is here. VCE. And then BC. BC is the point here. BC. VE is point here. VE. VB is point here. VB. And then VBC. BC. VBC is point here. Okay. So the silicon is mentioned, it is transistor. So it means that the value of VBE is 0.7. All right. So these are the informations that you have, and these are the informations that you need to find. Okay. So first of all, let's look the first step. And the value of beta is given equals to 50. All right. So first of all, what you need to do is, the first step is open all capacitors, remove all the capacitors, okay, and redraw the circuit, okay. Don't lazy to redraw the circuit, okay. Remove all the capacitor and redraw the circuit. So once you remove the capacitor, so the circuit will gonna look like this, right? So these are the circuits. After you remove all the capacitors, you open all the capacitors, yeah. Next, identify from this circuit that you have redrawn just now, identify the BE loop for you to decide the KVL, okay, Kirchhoff voltage law. So the BE loop is here. This is the BE loop. Okay, right. So the BE loop, VCC is given 20 just now. So 20, so this is positive, right? Positive. So positive 20. So here is positive, here is negative. These symbols too, these signs too, gonna help you in your exam. So don't forget to to sign this positive and minus polarity. Yeah? So this is positive, so this is negative, so this is positive, so this is negative. All right, so 20, the currents come out at negative, so minus IBRB, minus VBE, okay, because it's negative here, yeah, minus VBE, and then this is negative here as well, minus IERE. So we know this relation before, IE is equals to 1 plus beta IB. So replace this IE with these equations, yeah. So you will get 20 minus IBRB minus VBE minus RE brackets 1 plus beta IB equals to 0. Okay, always equals to 0. So this is Kirchhoff voltage law. Yeah, it's always equals to 0. So from here, okay, rearrange the equation and make the IB as the main. Okay, because you want to find IB, right? So IB will equals to 20 minus VBE. Okay, VBE is already mentioned, silicon just now. So VBE value is 0.7. Okay, so 20 minus 0.7 divide by the value of the resistor for each base and emitter resistor. So 430 kilo ohm plus 1 kilo ohm, 1 plus beta, where the beta value just now is 50. Right? So 1 plus 50, you will get the value of IB is 40.1 microamps. Right? So next, from here, how to find IE? Okay, so using the relation here, yeah, IE is equals to 1 plus beta IB. So you know the value of IB here, yeah. So IB is 40.1 microamps times with 1 plus 50 beta here. So you will get the value of IE is 2.05 milliamps. Okay, so be careful for here. Don't rush for you to solve this equation, because why? Once you get wrong answer for IB, you will get wrong answer for IE as well. And once you get wrong answer for IE, the others value also we're gonna get you will get wrong. Okay, so if you make mistake at the first step, your answer for the next questions also will becomes wrong. Yeah, so be careful at the first step here. Okay, slowly solve the circuit. All right. Okay, so next, once you get the IB, once you get the IE, all right, let's find the others. Okay, so from if you get IE, you will get IC as well, yeah, because IE and IC, the value is approximately same. Okay, so next, identify the CE loop. Okay, for the KVL, using the KVL. So the CE loops is here. Okay, now again, this is positive here. So this is positive, this is negative, this is positive, this is negative. So this is the CE. And then this is positive, and then this is negative. So using the KVL, so positive 20, okay, this is the value of VCC minus the potential drop because it's come out from negative, yeah, negative ICRC, and then minus the potential drop ID, resistor RE, so it becomes negative. Why? Because the current, at the end of the voltage is negative, yeah, negative IERE, and then, oh sorry, this should be negative. Okay, so this should be minus as well. Okay, minus VCE. All right. So since that we want to find the value of VCE, so rearrange this equation. So bring the rest here. Okay. So you will get 20. Bring the VCE here. Okay. 20 minus ICRC minus IERE. So IC value we already know. IC is approximately with IE. Okay, so IC you already know, the value, resistor also know, IE also we know just now, and the value of resistor for emitter is given. So you can calculate the value of VCE. Okay, so the value of VCE is 13.85 volts. Okay, so it is known that VBE is 0.7. So VBE you don't have to calculate. Okay, VBE, I think if the question asks you to find the value of VBE, I think it is a bonus for you. Okay, it is a bonus mark for you because it is always known that VBE, if it is mentioned for silicon, it is 0.7 volts. Yeah. Okay, so for here you don't have to calculate because this is common sense. This is what we have known before. Okay, so now how to find the value of VE? Here, the point at here. Okay, value of VE. So VBE, here is VBE. Yeah? So VBE equals to potential value voltage at VB minus with the potential at the VE. Okay, so that is VBE, right? VB and VE. Since these two, we don't know, but we only know this this value, so we cannot solve this equation. So we need another one. We know that VE here, okay, VE here is equals to currents that flow here, i.e. times with the value of resistor here, because this is from the Ohm's law. V equals to IR, right? So VE we can find because we know the value of IE just now. So VE is this value, right? So this one, we can find the value of VE is equals to 2.05. So once you know the value of VE, once you know the value of VBE, we can find the value of VB. So VB is equals to, by rearrange this equation, we will get that 0.7 plus 2.05. You will get the answer that the value of VB is 2.75 volts. Next, we need to find the VCE. Okay, to find VCE, we don't know the value. We know the value of VCE just now, 13.85, right? And we know the value of VE, so we can always find VC by knowing these two values, right? So we arrange the equation that we just now, and then you will get the value of VC is 15.9 volts. And value for VBC also, once you know the value of VB, once you know the value of VC, we can find the value of VBC. So it is minus 13.15, minus 13.15 volts, yeah? So this BJT, okay, if they ask you what comment the BJT. So now the BJT, how you want to decide it is a reverse active, saturation, forward active, or cut off, which it is in which region. Look at the value of VE, VB, and VC, right? Okay, so here value of VE is 2.05, value of VB is 2.75, so VB is higher compared to VE, right? So VB is larger compared to VE. Next, value of VC is 15.5, which is larger compared to VB. Okay, so so in which region of this transistor? So you can see here, yeah, VC is larger, okay? So here, compared to VB, and VB is larger compared to VE. So this transistor is working in this region now, forward active region, okay? So this BJT, bipolar junction transistor, is biased in forward active region, okay? So it is important for you to memorize this as well, okay? So that you can decide the BJT now is working in which region, okay? Right? So in which region is based from this value, yeah? These three value. Okay, so I hope clear, yeah, until here. So next, let's look how to plot the load line analysis for this circuit, for this emitter stabilized bias circuit, yeah? So for you to plot the load line analysis, first of all, we need to make sure, we need to decide that the VCE is equals to 0. Okay, so the transistor will be in a saturation region. Okay, in a saturation region. So taking the transistor saturation equation, okay, this is the transistor saturation equation where we same with before, if I'm not mistaken, but we just addition of RE. For a fixed base bias circuit, IC saturation is equals to VCC over RC, right? But for the emitter stabilized bias circuit, you need to consider the resistor at the emitter, okay? So now this is the saturation equation that will give you the Y-intercept value, okay? Y-intercept value. Next, we need to consider the cutoff, okay? When when the cutoff will happen, when the IC is equals to 0. So IC equals to IE. So VCE, VCE is equals to VCC. So this is the value of the x-intercept. Okay, x-intercept, x-intersects. Okay, so when you get these two equations, you can always plot the graph. So the graph this is the graph for fixed bias with emitter resistor. Yeah. So this is just now. This is at the saturation equation. Okay, this is the saturation equation, and this is the cutoff equation. Okay, cutoff equation. So once you get these two intersections, just connected the dots, and you will get the load line. This is what we call load line analysis. Yeah. Okay, load line analysis. So compare with the fixed base bias. Yeah, compare with the fixed base bias. For the saturation equation for the fixed base bias, we didn't take into account the resistor value at the emitter because there is no resistor at the emitter. Only VCC divided by RC, and then this is same. Yeah, VCC is equals to VCE. VCE. Okay, so I think this cutoff is the same. Only here at the saturation part is different. Yeah, for you to take point. Okay. So next. Oh yeah, this is the sorry. So this is the one the previous questions from test 2. Okay, test 2 during 2013-2014. Okay, so maybe you can try after this. Yeah, maybe you can try after this for you, just for your knowledge. Yeah. So this kind of questions will come up during your test 2 and also during your exam as well. So you can see each questions, especially for this question number 1, it carries lots of marks because you have to do lots of calculation to get this. So make sure in each operation, in each calculation, don't miss any numbers, don't miss any steps, because once you get ICQ wrongly, it will affect the value of the others as well. Okay, try to figure out this question after the class. Yeah? So this graph, okay, the value you can use based on this graph. Okay, if you see this graph, they in this question they didn't give you much information. They didn't give you the beta information. So beta you need to find from the Q point. Okay, how to find the value of beta? You need to find the value of the saturation first, yeah, from this graph. So try to figure out, yeah. So this graph is very important, okay, and this is at this part, yeah. At this part, this is the value of IB. This is the value of IB. So when we know, yeah, we know, right? IC is equals to beta IB. So this is the value of IC. So from here, this relation, IB and IC relation, you can find the value of beta. Okay. And I have enlarged this graph at this slide. Okay. I hope you can see clearly this graph at this slide. Okay, so try to figure out this exercise. Okay, perhaps this kind of questions with different value will come out during your test. Right? Who knows, right? So try to figure out these questions here. Okay, so next, what are the disadvantage and disadvantage of this emitter stabilized circuit? Yeah, so even though that this circuit is much more stable compared to the fixed base bias resistor, fixed base bias, it is still have a disadvantage where the current gain of B still can be sensitive. Okay, still can be changed because of the sensitiveness of the temperature. Okay, so it is not good. Okay, because it's still depending on this beta. So the actual value of beta is usually not well defined using this graph. Yeah. So how to overcome this problem? Okay, we need to develop a bias circuit that is less dependent or independent of transistor beta. So here comes the next circuit, which is the voltage divider bias circuit. Okay, so this circuit, it has an independent of the transistor beta, and it provides good Q point stability, okay, with single polarity. Okay, what means single polarity supply voltage? So what is means single polarity supply voltage? You can see here, this is supply voltage. Yeah, this is VCC, this is the supply voltage. So we are using the single supply voltage. Okay, so actually for fixed base bias and then emitter stabilized bias circuit, all that we are using the single polarity supply voltage. There is also another circuit where, okay, usually in voltage divider, we are using two polarity, okay, double polarity supply voltage. Okay, that's one we're going to look later on. Okay, let's focus on this single polarity supply voltage. So by using this single polarity supply voltage, you will get a good Q point where the Q point is stable enough. Okay, by adjusting the parameter of IB, okay, you will get a stable value for Q point. Yeah. So how? Let's look here. What's the difference between this circuit and other circuit? So you can see at this circuit there are extra resistor at this part. Okay, at this part where it connects the base to emitter. Okay, base to emitter, there are extra of resistor here. There's lots of resistor. Okay, so these are the difference between voltage divider bias circuit and stabilized emitter stabilized bias circuit. If emitter stabilized bias circuit, there's no this R2 here. Yeah, only RB here and RB and RE and RC. Okay, so how to solve? Let's look how to solve this kind of circuit. So the first step, as usual, you need to replace the capacitors. Okay, you remember, as usual, we need to replace or we need to remove this capacitor. Okay, ignore this capacitor. Okay, make it as an open circuit. Yeah, and then the second step, simplify using Thevenin theorem. So we're going to look later on what is the Thevenin theorem. Okay, and the third step, we need to locate two main loops, the BE loop and the CE loop. Okay. All right, next. So let's look at the first step. So the first step, locate capacitor and replace with an open circuit. So remove this capacitor, these two capacitor. So the circuit is going to look like this, yeah? The circuit is going to look like this, right? So R1, R2, RC, RE. Okay, so usually in voltage divider bias circuit, this is not represented as RB, it is represented as R1. Okay, R1, R2, RE, RC. Okay, next, after this, what should you do is simplify this circuit using Thevenin theorem at this part. Okay, so let's look how to simplify this circuit using Thevenin theorem. Okay, Thevenin theorem, also known as exact analysis. Yeah, it's also known as exact analysis. Okay, so first of all, we need to look at this part. Yeah, focus on this part only. All right. So this part, actually, it is a parallel. Okay, R1 and R2, it is connected parallelly. It is connected parallelly. Okay, so change this part to look like this. Okay, so you can see clearly that R1 and R2 is parallelly connected. Okay, so because currents that flow from R1, IR1 is divided into two. Yeah, once we're going to flow to base, one we're going to flow to IR2. So that's why it is connected parallelly. Okay, so redraw again this part, okay, and it will look like this. Okay, next, from there we can define, okay, define the RTH. What is TH? Thevenin, I don't remember, total for R total for this R1 and R2. Okay, so from here, first of all, you need to define this value of total resistor here. Okay, so make a short circuit. Okay, make a short circuit here. So R1 and R2, so this is parallelly, right? So we know that parallel, still remember, yeah, the parallel equation of resistor, it will look like, once you solve, it will be R1, R2 over R1 plus R2. Okay, these are the value of RTH. Okay, how to get this one? R1, R total, it is R1 plus 1 over R2. Okay, so rearrange this equation, you will get these equations. Okay, so here next, we need to find the ETH, okay, voltage source, okay, the value of voltage source. Okay, sometimes it's also mentioned as VTH, okay, same, V and E is the same, yeah? Only the symbols is different, only the sign is different, yeah? So next, find the voltage source, okay, where the voltage source is returned to the network and the open circuit Thevenin voltage. Now, we need to find the ETH, yeah? ETH at here, yeah? Also known as VTH. So how to find this value is V equals to IR, okay, so V at R2, ETH is same with the value of V at R2, okay, because this is parallel, right? So when parallel, the voltage is same, but the current is different. So ETH is equals to potential at R2. So how to find the potential at R2? We know the using the Ohm's value, yeah, Ohm's law, sorry. So you will get V is, of course, this V, yeah, VCC, and then times with the value of R, okay, R here. So you will get this kind of value. Later on, maybe you can figure out how it will comes like this, yeah. So VCC times R2 divided by R1 plus R2. Okay, so this is how you want to determine the value of ETH here. Okay, next, third step. Okay, so third step, we need to locate the two main loops, yeah. So the BE loop and then CE loop. So the BE loop now, it's like this, okay? It's no longer VCC now. It becomes ETH because you have already simplified, right? So it's no longer VCC, becomes ETH now, okay? And also it's no longer R1 and R2, it becomes RTH because you have simplified just now, okay? So the value of RTH and ETH that you find just now is very important, yeah? Once the value is different, this is also will become different. So this value, please careful, okay? So now the BE loops, yeah, we are taking this loop, yeah, which is clockwise loop. Okay, so we can determine now the value of IB, okay, currents that flow into the base, okay, by using the clockwise based on the Kirchhoff voltage law in this equation. So ETH, this is positive, right? This is negative. So positive, this is positive, this is negative, this is positive, this is negative, this is positive, this is negative. So minus IB, okay, currents that flow here is same, IB RTH minus VBE here, okay, minus IE, currents that flow at the emitter with the resistor at the emitter equals to 0. So IE is always beta plus 1 currents that flow from the base, yeah. So rearrange this equation by considering this value into here. So you will get IB is equals to ETH minus VBE, and then divide by total resistor value of R1 and R2 just now, and then plus beta plus 1 RE. Okay? Okay, so be careful of this one. Yeah? We are not considering VCC now for this voltage divider bias circuit. We are using the ETH now. Yeah. So VCE can be determined same as emitter bias configuration. So VCE same, yeah, no difference for you to find VCE. It's same as previous solution just now. Okay, the only different is BE loop analysis. Okay, CE loop analysis is same. Okay, because there's no difference for the CE loop now. Yeah. Okay, so let's look what even though it's same, so let's look together. So VCE can be determined same as emitter bias configuration KVL. Okay, using the KVL, so you will get VCE. How to find VCE is VCC. Okay, for VCE we are using VCC. Yeah? We are not using the ETH just now. We are using VCC. So VCC minus with the value of IC RC plus IE RE here. Yeah. So this is same with emitter bias configuration. So no changes. Yeah, only at the BE loop there is a change a little bit. Yeah. So next, so this is the value just now of IB, and this is the value just now for VCE. Okay. So this is the repetition actually. The summarize of how you to find IB and how to find VCE. Okay, so from here, based on this information, you can always find the value of VB, VC, and VE. All right. Okay, so let's look at the example here. Yeah. So find this is the voltage divider circuit. Okay, there are R1 here, R2 here, RC here, and RB here. Okay, so first of all, they said that the silicon transistor, it is a silicon transistor, so it means that VBE value is 0.7. Okay. Next, find the value of RTH, VTH, ICQ. Okay, so VTH is same with ETH just now. Okay, and then IBQ, and then VCQ. Okay, and those values as well. Okay, so let's look. Where is given for you, the value of beta is 140. Okay, so for the first step, okay, open all the capacitor, okay, and redraw the circuit. So we remove all the capacitor and we redraw the circuit. So it's going to look like this. Next, calculate the VTH. Okay, calculate the VTH here. Okay, so the VTH just now is VCC R2, yeah, R2 divided by R2 plus R1 if I'm not mistaken. So you will get this value. Okay, you will get this value for VTH. And then RTH is R2, R1, R2 plus R1. Okay, so you will get this value. So this is the value for VTH and RTH. Okay, and then redraw the circuit. Once you get this value, you need to redraw the circuit. So it will look like this. So where the value of VTH now is 2 volts. Value of RTH now is 3.55 volts. Yeah. So this is positive, this is negative. So current flow here, positive, negative. Current flow here, positive, negative. All right. So now decide the BE loop. Okay, so the BE loops. Okay, VTH plus IB. So this is the current. Okay, this is the current that flow, IB. Yeah. I think it is easier if you put the RTH here. Yeah? So you know that IB is currents that flow at the RTH. Yeah? So VTH minus potential drop at the RTH here. Okay, using the currents of base. And then VBE, we know the value of VBE, which is 0.7. Okay, VBE value is 0.7. And then IERE, then we know that IE is, is equals to 1 plus beta IB, right? And then replace inside here. Okay, so rearrange the equation, so you will get the value of IB, where value of IB is 6.05 microamps. Okay, next, using the relation of this, okay, you can always find the value of IE. Once you get the value of IE, you can get straight away the value of IC, because IE is approximately with the value of IC. Don't forget to write this, yeah, this information. Okay, sometimes, some of you want to skip the step. So when you get the value of IE, you straight away mention that the value of IC is 0.85 milliamps without mentioning IE is approximately 2 IC. Okay, so you're going to lose 1 mark here. Okay, usually this is 1 mark, this is 1 mark, this is 1 mark, another mark here. Okay, so please, don't forget to write this one. Okay, sometimes if this is not 1 mark, they still marks here, 0.5 or something like that. So please don't miss any marks inside your calculation. Next, once you get all those value, next you can, same as emitter bias, emitter stabilized bias circuit, you can always find the CE loop. Okay, so the CE loops, when you know the value of IC and IE, you can find the VCE. Okay, so the value of VCE is here. And then since that you know the VBE here, okay, and you can always find the value of VE. Okay, so once you know the value of VE, you can find the value of VB. Okay, so VB, once you get the value of VB, and then you get the value of VE, and then you can find the value of VC. Okay, you can find the value of VC, and then from here, we can also find the value of VBC. Yeah, because we already have this two value, we can find the value of VC. Next, you can decide either the BJT is in which region. Okay, in which region just now. Okay, reverse active. This is reverse active region. This is cut off. No, this is saturation, right? Saturation or cut off? I don't remember. Saturation. This is active region. This is active, forward active region. I think this is saturation and this is cut off. But please check later on, okay? So how to decide which region the BJT is working in? Okay, it's looking by the at the value of VE, VB, and VC. Okay, so since like the value of VC is larger compared to VB, and value of VB is larger compared to VE, so it is in a forward active region. So this BJT can be applied as a amplifier. Okay, it can be applied as an amplifier. But once the BJT is biased inside the saturation or in a cut-off region, so it can be applied as a logic switch. Okay. All right. So I think it's clear for this. Yeah. Okay. Let's move forward. Okay. For this kind of circuit, try to solve it step by step. Okay, don't rush and slowly solve this circuit. Even though it is look like very complex, the circuit, but it is not difficult enough. It is not too difficult to solve the circuit. If you follow the step accordingly. Okay, so next, look the other example. Okay, this is other example. Okay, for this example, okay, be careful. For this example, there are two supply voltage for this circuit. Now, this is what I said just now. For just now, for example 1 that we have done just now, there are only one supply voltage of VCC. Only one supply voltage here. But for this example 2, there are two supply voltage, VCC and VEE. Okay, so let's look. Okay, so next you need to determine as usual IB, IC, VCE, VB, and VC, VE. Okay, VB, VC, VE, VCE here. Okay, VCE here. IC that flow here. Okay, and then IB that flow here, and that's all. Okay, so it's given to you that beta is equals to HFE, which is 120, and VBE is 0.7, or it is also a silicon transistor. Okay, and this is the answer. All right. So let's look how to solve this kind of equation. First of all, open all the capacitors and draw the DC equivalent circuit. Okay, so remove when you all this capacitor inside this circuit. Okay, so it will left you this figure only. Okay. Next, calculate the VTH and RTH. So VTH and RTH same as before, but you need to considering the here. Okay. So VTH R2 equals to R2 times with the VCC. This positive is referring to the polarity of the VCC. Yeah? It means that the VCC is positive. The positive value of the this source. Okay, this negative is referring to this source of voltage. Okay, so so if you look here in this VTH, there is additional of this part. Okay, this is same with single. If a single polarity of voltage source, you only considering this part. But since that there are two, so you need to considering this part. Okay, so it is minus. Okay, plus with this part. Since the voltage is minus, so it will be. This is VEE. Sorry, this is VEE. Just now. So it will be just replacing the value. So you will get the value of VTH is minus. Okay, minus. Why it is minus? Because it means that at this part, the voltage source at this part is higher compared to this part because of the resistor here is much lower compared to the resistor here. So it means that the voltage is flow from here to here. The current is flow from here to here. Yeah. So next, Allahu Akbar, sorry. Next, from once you get the value of VTH, yeah, don't worry if you get minus. Okay, it just a sign of which direction of the voltage of the current flow. Yeah, so for here it means that the current flow from the VEE just now. Yeah, so RTH so same. RTH I think it same. Yeah, RTH the total resistance value will not change. The formula is same. Okay, only the VTH is different because you need to consider this part. Okay, so now once you get these two value, okay, decide the BE loop for the Kirchhoff voltage law. So the BE loop now you have to considering the VEE as well. Okay, so the VE loop will looks like this, right? And then this is the positive, and then I'm only drawing at this part, yeah? And then here, and then there is another voltage polarity here. So it is like this. Okay. And here, tak ada ground, no ground. So if you are taking like this, so this is VCC. So the currents come up positive, right? Positive, negative, positive, negative. Currents enter here. This is at the base. positive, currents come out here, negative, positive, this is E, negative, then positive, this is minus sign, so it's come out minus. So if you are taking clockwise, so it will be VC, Allah, 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 Allah. Stop. Oh, I need to draw it again, wait, I positive, and then this is and then positive. Okay, so this is positive, this is negative, positive, negative, positive, this is B, and this is E. This is positive, this is negative, this is positive, this is negative. So by taking the clockwise, so it will be, this is VCC, right? So VCC, this is, sorry, this is not VCC. This is become VTH just now. So VTH, this is VEE. So this is RTH. Okay, so this is VBE. So this is RE, right? So the Kirchhoff law, we're going to be VTH minus IB RTH minus VBE minus IE RE minus VEE here. Okay? Equals to 0. Oh, this is positive. It's not negative here. Yeah, negative. Negative. So it means here is, sorry. So it means here, contoh mata ni, korega positif, korega negatif ni, positif minus korega koko kara ni, negative. Oh, sorry. Yes. This is negative and this is positive because currents enter here is positive, currents enter here is negative. So dia hantai ni, it's the other way around. So it will be like this just now. Positive, positive, ITH, and then positive. Okay. So it will be like this. So this is VTH. So the RTH. So this is B, this is E, VBE. So this is positive, this is negative, positive, negative. And this is RE. So this is negative, this is positive. Sorry. Yes. So the VTH plus minus IB RTH minus VBE minus IE RE come out positive, positive VEE. Okay. Alright. Okay. So from here, okay, we are still using the same relation. Okay, to replace the value of IE. Okay, so next from here we arrange the equation. Okay, we can find the value of IB or IBQ. Okay, so you get the answer 35.35 microamps. And then from here, once you get the value of IBQ, you can always find the value of IEQ. Okay, IEQ. Once you get the value of IEQ, you can always get the value of ICQ. Yeah, right. So these are the quick answer. Next, using the CE loop. Okay, from using the CE loop, we can get the value of VCE. Okay, we can get the value of VCE. Okay, with using the same value of currents that flow from the collector and emitter that we have found just now. And then using that, we can find the value of VE, right? Because using the value of IE. And then once we know the value of VE, we can find the value of VB, okay, by using the value of VBE is 0.7 volts, yeah? So once you get the VB, okay, once you get VB, we can find the value of Okay, so you get the value of VB. Oh, sorry. Once you get the value of VB, next you can find the value of VCE. Okay, so VCE is based from this value. Okay, and then VE is based from this value. Then you will get VC is equals to this. Yeah. All right. So next, if you want to comment of the resistor, okay, look, the resistor now VE, VB, and VC. What is the value? VE is minus 12.3 volts. VB is minus 11.6 volt. And then VC is 8.44 volts. Okay, so it's still in an active region, right? Because this is higher compared to this is higher compared to this, okay? Because this is minus sign, okay? So this is higher compared to this, right? So it is still in a forward active region, and it can be applied for amplifier. Okay, if they ask what are the application for this transistor, so it can be applied as an amplifier. All right. So next, okay, this is the example of questions that come out during the final exam. Okay, in year 2010 and 2011, long year ago, 10 years ago. Okay, so this kind of questions come out. Maybe you can try. So this is to polarity, to voltage. Now, to voltage source. Okay, VS and VCC. Okay, so maybe after this you can try to solve this equation. Okay, it's already given to you the answer here to check your to check your answer. Okay, you can base on this answer here. Yeah. All right. So next, let's move on the approximate analysis. Okay, just now, we are using the Thevenin theorem using exact analysis. There are actually two analyses, okay, which is exact analysis and also approximate analysis. But approximate analysis is rarely to use inside the circuit calculation, okay, and also will not come up during your exam as well. So this is just for your information, okay, approximate analysis. So for approximate analysis, the extra that you need to consider is there is a resistance Ri that equivalent to the resistance between base and ground, okay. Between base and ground, at the base and ground, there is another resistor Ri that you need to consider. So, but to use this approximate analysis, what we need to see first, there is a law. There is a condition that you need to see first if you want to use this approximate analysis. So, to use this approximate analysis, this condition must be satisfied. Okay, where the beta Re, okay, the value of beta for resistor at the ammeter must be bigger or larger 10 times compared to the resistor R2. So if this condition is fulfilled, then only we can use this approximate analysis. Okay, so you usually value of beta is given inside the circuit, right? So value of beta times with the value of resistor at ammeter, okay, and then if it is 10 times larger, okay, at least 10 times larger, yeah, or it can be much more greater, but it should be larger than 10 times the value of R2. Then only this condition, approximate analysis, can be used. Okay, so once this condition is satisfied, we can always say that the value of ETH or VTH just now is same with the value of VB. Okay, so you don't have to calculate the value of ETH. Okay, you only need to calculate the value of RTH only, okay, because the value of ETH is equals to the value of VB, right? In this approximate analysis, right? So for this approximate analysis, yeah, I repeat it again. For you to use this kind of analysis, okay, if you want to decide which one analysis that you want to use, either exact analysis or approximate analysis, first of all, look at the value of resistor, beta times the resistor value at the emitter. If it is 10 times larger, okay, 10 times larger to the resistor value of R2, then you can always use this equation, this analysis, where you don't have to calculate the value of VTH or ETH. It is straight away value of ETH is equals to value of voltage at the base. Okay, so you need only to calculate the value of total resistor. Okay, but this will not come out in your exam. Okay, this will not come out in your exam for your final test or test 2. Okay, so this is just for information that there is also another analysis that you can consider, which is approximate analysis. All right. Okay, I hope this is clear. Yeah. So next, how to draw the load line analysis for the voltage divider bias circuit. Okay, so in order for you to draw this line here, first of all, we need to find the intersect of x-axis and also intersect at the y-axis. So same as before, okay, to find the intersects of y-axis, you need to consider the the saturation, okay, saturation region. To find the value x intersect at the x-axis, you need to consider with the cut-off region. So the cut-off region, it means that the value of VCE is always value of VCC. So this has no changes. Yeah? This value for you to find the cut-off region is no changes with the emitter stabilized circuit. Okay. For the saturation region 2, okay, it is not different with stabilized emitter stabilized bias circuit. It's same. Okay, VCC is equals to RC plus RE. So once you get these two value, okay, so this is y-axis, this is x-axis intersections. Connect these two points, so you will get the load line analysis. So next, I think for today we can finish earlier because after this I have training. So for this DC bias circuit, okay, how about DC bias circuit? Okay, all this while the types that we are using, the transistor type, BJT transistor type that we are using in the circuit, all is an NPN type. Okay, NPN type configuration where the currents come out through the emitter. Okay, currents come out through the emitter. How about PNP? How about the PNP types of transistor? So all this while, the previous analysis and the previous techniques that we have discussed before, it is applicable as well to the PNP BJT. Okay, it is applicable to the PNP BJT, but the things that you need to consider is the current's direction. Okay, the current's direction. Okay, only the current's direction is different. Okay, because for the PNP, the currents is flow from emitter to base and collector. But for NPN, the currents come out through emitter. Okay, so why it is applicable? Because you can see that the amount of currents is same for both of them. Yeah, IE is equals to IB plus IC. IB plus IC is equals to IE. So it is applicable. Okay, all the techniques, all the methods is same. Okay, so when they say that the transistor configuration PNP, so don't say that you don't learn. Don't say that you don't know. Okay, it's same. Okay, but the only difference is the current direction. All the methods of calculation is applicable. It can be used. Yeah. So the PNP BJT currents flow from emitter to collector. Okay, from emitter to collector. Okay, to base and collector. Okay, but for NPN, it's the current flow from the base, okay, to collector and emitter. Okay. So up until now, any questions? Any questions or this is for those who didn't just tak sempat just now, yang tak sempat scan the QR code. You can scan the QR code now. Any questions up until now? Oh, by the way, if you realize in your e-learning, I make a survey. Oh, ada chats. Yeah, Sensei, I don't understand the part finding BTH. Oh, sorry. Go. It's very hard. Which part just now? I didn't realize the message. The exact part. Well, wait, yeah. Okay, I answering the questions first, and then later on I will go to the survey. This part, which slide? The exact. This one. Is it this one? Is it this slide? Bukan ni. This one. This one, right? The one with 2 volts. The 2 volts. The example 2, yeah. Okay, this one, yeah. Okay. Which part you didn't understand? This one. So this one is okay, right? This one is okay. PTH. So which part you didn't understand? VEE and VCC. Why VCC time R2 and VEE time R1? VEE time R1. Yeah, we're gonna look at it. I think we should VEE time R1, VCC time R2. Okay. So let's draw the yeah. Okay, now let's look here. We are using this one, yeah. We are comparing with this one. Okay, we are comparing with this one. Okay, let's compare with this one, yeah. So this one is 1 voltage source, right? So voltage source. Now, if you have 2, let's say that we have 2 now. So I need, I don't remember just now. How to go to find the. What happened? Oh, okay. Sorry. Sekejap. Sekejap. Ya. Sekejap. Wait a moment, okay. Okay, so not this slide, right? Ada voltage divider. I need to record that. I need to record this one. Okay, so this is VCC, right? This is R1 and this is R2. Okay, so let's look at the next slide for this one. Okay, so now for here, okay, so I wrote so I write about for if it is 1 voltage source, yeah? If 1 voltage source, it will be like this, right? VCC R1 and then R2 and then here. This is R1, this is R2. The ETH is here, right? So it is same with VR2 here. So this is VCC, okay? So in this case, we have VE additional here.
Sensei.
Yeah? It is not here.
Okay.
Okay, sorry. Jangan. Lupa dah. Window. Okay. Nampak kan? Okay. Can you see? Okay, so one voltage source. So the ETH is here, right? Okay, the ETH is here. So for two voltage source, yeah, now we have to considering the VEE. Two voltage source. VCC. R1. R2. And the voltage source, another one is here, which is VEE here. VCC, VEE. So this is R1, R2. So here is ETH. Okay. So now let's look here, yeah. For us to find ETH, it will be, for this, it will be, for this, it will be VR2, just now, VCC times with R2 over R1 plus R2, right? So for this one, since that we need to considering the other voltage source, yeah, I show you. Okay. Jai. I show you this one. Yeah. Wait ya. Kejap. Tak apa. So it will be how just now? Okay, so it will be for this part, yeah, ETH, it will be R2 currents that flow here. Currents flow here. The currents is flow here, right? I.e. IR1. So IR1, I that flow to IR1. IR1. ETH is equals to this value, right? So VR2 is equals to IR2 times R2. Okay, and then from here to find IR2, okay, IR2 is related to, let's see, go. Can I show you later because I have training after this. Can I show you later on after this? How to get ni? Oh, because I already late to the training. Is that okay? Okay. All right. So later on, I will put inside the e-learning how they solve these equations. Okay. Okay. Together with the recording as well. All right. So after this, not after this. Yesterday I already put inside your e-learning about the survey for test 2. Okay, so test 2, I'm doing survey if which time that you prefer. First, if like before test 1, we are doing during the class time, or separate day where you it is not a time not time limited, okay, but in one day you have to key in the test. Okay, so please choose either two. Okay, please make a survey. So because I'm considering to make the test two will around next week. Okay, where we cover the chapter apa rectifier and also BJT DC analysis. Okay, so can you make your survey? Some of you already make, but for the rest, yeah, can you do that? All right. Okay, oh ni lambat sangat ni Vikram. Okay, so I end the class earlier today because I have training after this. So for those who just join, you can scan the QR code, yeah. And I will send also the solution for Go questions just now later on. All right. Thank you so much. Assalamualaikum.
Waalaikumsalam, Sensei.
Thank you, Sensei.
Thank you, Sensei.